Welcome to the plenary hall for this sort of early afternoon session. Our first presenter for this block is Richard Jones. He's a Python programmer with nearly 15 years experience. He's an occasional core developer of Python itself. He's a member of the Python Software Foundation. He's a co-founder and chair of the program committee of PyCon Australia, which means he picked his own talk, you know. And this time he's learned a few things about what you should not ever, you should absolutely not ever, ever, ever do. Please welcome Richard Jones.
Thanks, Benno. Okay, so this is just going to be a fun little talk. Well, at least I thought it would be fun. I hope you get a bit of fun out of it too. And basically what I'm going to do in this talk is poke around some strange corners of Python and perhaps show you some things you can do with Python that you probably shouldn't do. But maybe solve some of the... Sorry? Yeah, well, we'll get to that. You might learn something new, which will be cool. We'll see how we go. The first thing I'm going to look at is a couple of corner cases of the Python grammar that kind of surprised me. I thought they were kind of neat. We'll see how we go. So let's say we have serialization, right? Turning data into text for storage or transfer or whatever. We have some mix-in classes that perform serialization. We have our preferred mix-in class, which might not be available, so serializing to JSON is preferred over serializing using Marshall. But we want things to keep on going and rocking regardless of whether, a preferred one is available. So did you know that the classes in the bases clause of a class definition can actually be an expression? Because inheritance doesn't really cut it in this modern world of rapidly changing serialization protocols. We need fallbackitants. Okay, who knew that the except clauses of can be expressions as well? Whatever the expression evaluates to had better be an exception class, or it won't work. But as long as it is, the exception type that you end up with will be the thing that's caught. Okay, so keep that in mind. Generators are cool, right? When you pluck the double under next out of a generator, you can just keep calling it, and it just keeps generating stuff. They're like little happy spewing machines that make your program awesomer. They just keep generating. They're awesome. Let's modify our generator to generate exception classes instead of strings. So now we have some stupid code that generates some stupid assertion errors, but about half the time. And we can restrict our program so that it just catches some of them. And after 5, we stop squashing them. So that's a bit dumb. This is an actual line of code from MongoDB. It isn't exactly the same thing, but it's kind of similar, which is basically squashing the logging of an exception for roughly 90% of cases randomly. So that's fun. Okay, so that's just a couple of bizarro things in the grammar which I thought pretty cool. Python's also quite famously mutable. So let's look at some things in Python's runtime that are perhaps a little bit more mutable than you might have previously thought. Let's start off with a little function, okay? We'll call it f, and it does a thing. The thing it does is in its code object, and the code object is attached to the function object as the dunder code attribute. You can exec code objects, that's fun. We'll come back to that. So we'll make another function now, and let's call that g. It does a thing as well. So how many of you knew that the dunder code attribute was mutable? You can take the code object from one function and assign it to another function. So that's fun. The code object is not unique to functions. The code in modules is also encapsulated in a code object. Module objects have a dunder code object. The PYC files that are written by Python to cache module code is actually that code object marshaled using the built-in Marshall module. And we can unmarshal that object. And I think you probably know where I'm heading with this. So that's, that's fun too. That's some mutability that you might not have known about. You can also create code objects by hand. This is actually an unrelated conversation, but it's similar. This is where we start going off the rails. And of course, you can start with Python code to create code objects by hand, but that's the obvious way, right? We're not talking about the obvious way of doing things. We're talking about XML, the beautiful elegance of XML, Python XML. We'll call this file adder.pi xml. Isn't it beautiful and elegant? Oh man, I've got a whole bunch of XML stuff here. I'm not going to even try to. So what we're going to do is we're going to parse this XML using element tree, which is nice. And we're going to construct a thing called an abstract syntax tree, which is a built-in thing in Python. And we can take that syntax tree that we build and we can turn that into code using compile. And it basically consists of a bunch of this. I have it on good authority from someone close to the AST code that this really isn't done very often. I even managed to provoke a seg fault from deep inside AST, which kind of worried him. But I'll get back to, I'll try and figure out exactly how I did that. It's pretty straightforward, really. We're just visiting elements in our element tree and constructing the appropriate AST object or node for the thing that we find in the XML. It's fairly straightforward. There's some things I kind of fudge here, like the line number and the column offset, which I probably could have set if I spent a bit more time poking around element tree, but that's not the interesting part of this. Okay, so that's fun. So let's make this glorious new possibility of Python in XML a reality and install a Pi Xml Loader. So now we can import adder.pi xml. And it's actually pretty easy to do that too. So to do all of that, we create a custom importer file loader for the import machinery. The import stuff needs me to register a finder, which will locate the Pi XML file matching the module name that's being imported. And it returns a loader, which can load the module and give back a code object. So you can see it's pretty straightforward. You can, and we just use the AST from XML thing I just showed you to turn that text file into a code object. You can also abuse this. I have it on good authority. The very clever man has used this this sort of approach to actually allow loading of SQL files into Python using import and making them executable inside Python, SQL files. So that's kind of neat. You can even you can write funny little DSLs that meld Python and Lisp, which has been done. You can write something to implement macros using this sort of thing, which again has been done. Yeah. Okay. But I think that we can throw in, we can do worse. We can throw in some of Python's slightly more powerful introspection capabilities as well, and we can see what sort of damage we can do with those. So we'll start off simple. So you know about locals and globals, a couple of built-in functions that give you access to the local namespace and the global namespace of where they've been called. They give you a handle on a dictionary, which has got those namespaces in it. Or as I like to call them by their full name, inspect current frame.f under locals. There's another one which is f under globals, which is the global namespace. Anyway, you can poke at that dictionary just as like it was a dictionary. And here's a hint, it's a dictionary. So you can modify the dictionary to create new local variables just fine. All right, so let's say that we had some JSON called config.json. You might know where I'm heading with this. So now we can define an import JSON thing that loads those values from the JSON file, imports them into the current namespace. So that's handy. And it's actually pretty simple too. I mean, why should import star hog all the namespace pollution fun? We can look up the call stack to find the local namespace of interest. The inspect module provides all of this stuff. We get the current frame. We go back one step to the caller of the current frame using fback, and we get its locals using flocals, and then we just update that dictionary with all of this. This is not the worst thing I'm going to show you today. But it's probably worth saying you probably shouldn't do it though. Okay. So another type of mutability that may be unexpected. Let's go back to the serialization idea, right? We've got these serialization classes. We've got this setup where we've got do stuff and it's doing stuff, and it inherits from the mixing class to serialize using the Marshall module, and that's all good. Let's say we decide a little bit later in our code that we want to stop using Marshall to serialize the data and we want to use JSON instead because it's easier to read. And that's nice, and we can just switch over to it. And we can do that. We just swap out the old mixin class and swap in the JSON class. And so do stuff just starts using the new mixin class because that's its base class now. Okay, groans, excellent. So, context managers, right? They're pretty neat. So who else, when they first saw context managers, thought, hey, I could do namespace stuff with this? Just the two of us then. Okay. Well, I certainly did. Okay, so here's a context manager that'll snarf all the local variable assignments and copy them into a dictionary called D. Think of it as kind of a backup namespace or something. I have no idea why you'd want to do this. I'm not going to justify it. It's just a thing you can do. It's pretty easy to modify that code to capture the locals onto another object. So no more typing self all the time. And who else is sick and tired of typing global all the time, right? Well, we can do away with all those pesky global variable declarations. Promote everything up to global. And again, this code is pretty simple. It's pretty relatively straightforward. So if you recall, our context managers are invoked twice. The enter is invoked at the start of the with block. So when that happens, we snapshot the local variables, the names of the local variables belonging to the caller's frame, as in the thing that called enter, using fback and flocals, just like we did before. And then when the with block exits, we figure out what are the new local variables and we capture them. Straightforward. Okie dokie. So I'm going to take a bit of a diversion here. A common problem we have as software developers is that we're often asked to find out why some live code has gone awry. Sometimes we're not the author of the code, and sometimes we're not even familiar with the deployment scenario, and sometimes it's late at night and we're just not happy at all about having been called up to fix somebody else's mess. A clever lad called Ka-Ping Yi has created a module to help us out. So we go into this code that we're trying to figure out what's going on, and we put in a print statement, right? We've got the print out the web query thing or whatever, but the problem is we have no idea where standard out is going. So then maybe we try standard error, because that'll go to the log file, right? Except it doesn't end up in the server. We can't figure out where the server logs are, or it's just not appearing, it's being squashed, or it crashes the server. That's fun too. So we try logging, but seriously, there are so many ways that this can fail. I mean, you don't know where the log's going to go. You don't know what the logging level is set to. It's just a complete joke. So Ping invented Q. You pip install Q, and then where you want to inspect something in the code, you say import Q, Q-foo, and that will dump out to a file in /temp called Q, a thing saying foo equals and its value. So some code like this, when run, we call spam twice with a couple of different values. The Q module will tell us what the expression was that we inspected with Q by calling Q, and it'll tell us the value, and it'll tell us the function that it was called in. That's really handy. It also has another behavior where if you use it as a decorator and decorate a function with Q, it'll trace some information about how that function was called and what its return value was. So again, same example, but decorating the spam function this time. We see it's called with different arguments, return different values, and the inspections inside the function are indented nicely as well. It's clever if the return value is huge. So if you're doing this on an actual web application, you're returning a chunk of HTML, which is huge, it'll just say, okay, that's a big amount of content, it's in this file here. So it stores it away in /temp in a different file. But you may have noticed there's probably some funky stuff going on here with Q. One of the things that it's doing is that, okay, who's familiar with decorators, right? Yeah, and the basic idea is decorators are things that are called on functions. Okay, so how do we know when it's being called as a thing to dump out a value or when it's being called as a decorator? Well, that's what this code does. This determines whether we're being invoked as a decorator or just as some value dumping function with a callable argument. It walks up the call stack to see where, and looks at the actual source code of the call site, and if the source code says @Q, then we're a decorator. It's perfectly reasonable. Okay, Q does a bunch of other stuff that we'll come back to. Let's take another diversion. This is Java. Don't do this. Okay, so back when I was teaching Python at university, I had a student who asked me how to do overloading of methods like Java does. So for those not familiar with Java, it allows you to have multiple methods with the same name, different signatures, and when you invoke the method, Java figures out which implementation to use based on the arguments you pass to the function or the method. So he asked me how you do this, and I said, Python doesn't do it doesn't work that way. We do mutability of arguments a different way. And I had to think. I said, I'll get back to you next week. So then I wrote overload, which allows you to overload methods. So you decorate the first method of that name, say this is the first implementation, then you add other implementations of the method to the overloading. And then when the method is invoked, we figure out which arguments match which particular signature, and the correct one is called. You can overload functions as well, and you can use function annotations in Python 3, and it'll make sure that the types match. You can even overload class methods and static methods and classes if you really want to. And it uses a bunch of really neat introspection that Python offers. So functions, for example, they have a dunder defaults attribute which tell you the default values that were defined when the function was defined, when the function was created. The function's code object tells you how many arguments that code object is expecting to be passed and what their names are. We match arguments passed into the function to the function signature using basically the same method as just a regular function call, but trying to find the first function signature that accepts the arguments that are actually being passed in. So for each element in the arg count, we pop an element off of the arguments that have been passed in, and if there's none of those left, then we can look up keyword arguments based on the var names. We can also look at the function's annotations, which is a dictionary that gives us, we can look up the named arguments using in the annotations dictionary to see whether there is an annotation. And if the annotation is a type object, then we make sure that the type matches the argument that's been passed in. The code object has some flags. This one says that the code object accepts variable arguments, so star args. And this one says that it accepts variable keywords, so star keywords. And once we've matched the the implementation that will happily accept all the arguments that have been passed in, we can call it. We do have to throw in another additional hack in there because static methods and class methods actually have a kind of a proxy-ish sort of a thing that means they're not actually the thing that you want to call. But it's pretty straightforward. Okay, so back to the Q module. It's really neat, but there's something not quite right about it. Who can see what's wrong with this? Modules aren't callable. Okay, to make this work, the Q module resorts to a bit of a hack. The implementation of what the Q module does is encapsulated in the Q class. So what we're doing here is we're taking an instance of that class and replacing the module in sys.modules with an instance of that class. This has some side effects. Most notably, as soon as you replace the module in sys.modules, the module is garbage collected. Because there's no references to it anymore. The Q class does not keep a reference to its module. The import hasn't completed, so the thing that did the import hasn't got a handle yet. So it goes away. So therefore the Q class has a bunch of really yucky hacks in it. So all of the imports are done in the class statement itself, the class definition. So all the modules that are imported that it uses are all class attributes. It has to define a dunder name attribute so it can pretend to be a module so that Google App Engine is happy. And there's a bunch of other stuff in there as well. So I propose there's an alternative. We just need to make modules callable. So, given a thing that we can call hello world.py, let's import callable modules, enable callable modules, and then we can define a dunder call function, and when we import hello world, we can invoke hello world, and it's callable. Hey presto. I'd actually argue that this is something that is actually not that bad an idea. The idea, that is, of having these dunder methods as class function, as module functions, is actually kind of handy and useful. It'll never fly, but I think it's a good idea. But so how does callable modules enable work? That's kind of weird. Okay, so the handling of callability is done at the types level, as in C types level. Every built-in type like ints and modules have a Pi type object C structure. Callability is implemented through a slot in that structure called tp_call, which you can see just down the bottom here. It's a ternary func. It's appointed to a C function that is invoked when objects of that type are called. If it's not set, that is, if it's null, then objects of that type are not callable. So we need to provide a callable for the TP call slot that implements ternary func, that signature ternary func, and a way to assign it to that slot using C types. So, first up, we have to define the callback. So we define the ternary func thing. We have to define the C level API for C types for the ternary func callback, and then we define a very simple callback Python function, which we'll use as that callback, and that just implements calling dunder call on the object that the callback is being invoked on, which in this case the object will be a module. The C types layer does some interesting things with Python callbacks for C functions that I won't go into the nitty-gritty details right now, but suffice to say that the ternary func takes 1, 2, 3, 4 Python objects, except the last one is optional, so it might be null. So I can't declare it as Pi object, I have to declare it as C void P and then do some casting stuff down here. Anyway, it's just a bit pretty. It took me a little while to figure that out, but I got there. Okay, so once we've got that, then we need to define the structure for the type object, or at least enough of it so we can get down to the TP call bit. We don't really care about the rest. We just need to know what the offset is, so hence everything else is a void P. It's just a pointer that we don't care about. We just need to be able to assign to the TP call slot. We also need Pi object defined so that we can actually get to the type object. Pi object is actually really interesting. It only has two slots. It's kind of neat. So once we have all those parts in place, we can modify the module type to make its instances callable. And we get to the module type through well, we've already imported C types, so we might as well use that as our module of choice. The ID function tells us the memory location of the Pi object in C, and so we can grab the Pi object using that address, and then we do a few modifications. Hey presto, we can assign our module call. And so we can import callable modules, we can do all of our things, we can import string, attach a call to it, and then we can invoke the string module. So that's neat. It's a little bit wrong, but it's neat. Okay, we're not done yet. So using similar C-types hackery, we can modify built-in types to add new attributes. And this has actually been done by somebody else. And it's a thing called forbidden fruit. And it's on GitHub if you really want to look it up. It defines a function called curse. And we can use curse to add new attributes to things like the int object. So here, for example, we're adding days to the int object, which returns a time delta of that int value of days. And we can curse time delta, which is also a built-in object, to return ago. So that's kind of neat. We can say 12 days ago. This is inspired directly from Rubyland, of course, and it's a little bit wrong. That's all I've prepared for you today. I would like to say thank you to Ryan Kelly and Nick Coughlin for their assistance in developing this talk. And I do have some time for questions, although I have no idea what your questions might be and whether I could answer them, but please feel free.
I'm not sure whether to phrase this as a question or a statement. I'm going to go with statement. Please tell me you have not used these in production.
Oh, no, hell no. Although Q, yes.
No, okay.
Why?
Because it's a heck of a lot of fun. I had so much fun making this.
Okay, so moderately seriously, the reason why all this stuff is possible is because Python is an incredibly reflective language and has all these internal hooks which are useful for things like debuggers to get into and can be useful for various reasons. Now, you've obviously shown the worst possible examples of, oh my God, what the hell were you doing? But
I've tried.
I mean, some of this is just a case of with great power comes great responsibility. So there's not really a reason to take any of this out of the language. It's just, so you're not actually...
Well, and a lot of these things have been added to Python over time. Things that, things like the mutable local and global namespaces, they weren't originally. That's been added, and it's incredibly useful. The AST stuff is a recent thing as well. You know, that's been added, and that's incredibly useful. And you can do good things with it. You can do stupid things with it too, and that's what I focused on. That's fine. I actually do have a use case, by the way, for callable modules, and I'll walk you through it because I've got a couple of minutes. So I have this module I wrote called HTML, and it's pretty basic. It just allows you to create HTML text from Python code using a relatively nice syntax. You grab a HTML object, you say html.body.p with some text passed in, when you call it with some text, and that'll create a HTML document which has a HTML tag, a body tag, and a p tag with some text inside it. It has attributes and it has a lot of stuff. It's really nice. And I wrote it to be Python 2 and Python 3 compatible, so it can actually run under both. The problem is Python 3 decided to co-opt the HTML namespace for itself. So in the Python 3 standard library, html.quote, I think, is the module. No, sorry, the HTML is the module, and it has things like quote and unquote, I think, are the names of the functions that are defined inside it. And because HTML has been defined as a module, nobody else can use the HTML namespace to implement a package, which I think is a bit of a shame. Now, if we took those two functions out of the HTML module, we made HTML a package, and quote and unquote were just modules that were callable, then I could create a write module, HTML.write module that could be installed in the namespace alongside them, and that would be neat. And also Q, Ping wouldn't have to resort to these ugly hacks to make Q callable. So I think there's a valid, justification for it, but I really don't think I'm going to win the argument. Nick doesn't think I'm going to win either.
Let's keep that ability one. No, that probably wouldn't fly. That's your best bet, though.
Anyway.
Are there any other questions?
Oh, wait a second. Uh-oh.
So if you've ever programmed in Java before, you might have this strange idea that a file should correlate to a class.
And then if you try and translate this idea into Java, you'll always have in your imports, say, from site, import capital site. So I'm wondering if it'd be a good or bad idea, depending on your
Well, there's an awful lot
opinion.
of, Overload is another example. There's an awful lot of modules out there, Python modules, they do one thing. And they have one thing that's callable inside them. So there's always from overload, from queue, import queue. All these things all do this from something, import the thing that does something.
So surely it would be a good idea to make that a little more convenient.
Yeah, I still don't think it's going to happen. Anyway, yeah, I'm not going to go into the curly quotes as valid Python syntax.
Yes, let's not. Thank you again, Richard Jones.